In this video, we're going to explore how to differentiate exponential functions. The natural exponential function is y is equal to e to the x. And to evaluate its derivative, we're first going to consider the derivative of any exponential function. Recall, an exponential function is just a base to the exponent, b to the x, where that base is a positive real number other than 0 or 1. So here is our limit definition of the derivative. It is rise over run as run goes to 0. For this particular function, f of x is b to the x. So f of x plus h, f of x plus a little bit, is just b to the x plus h. Inputting an x plus h. All right, and that's all we have right here. There's your f of x, and here's your f of x plus h. Okay. Now just using a little law of exponents from here to here. B to the x plus h is b to the x times b to the h. Those are h's, right? 2 cubed plus 4 is also 2 cubed times 2 to the 4th. Base is the same. When you're doing that multiplication, we get to add our exponents, right? Here they just factored out that b to the x. Right? B to the x times h is b to the x times h, and b to the x times minus 1 is b to the x. And here, I'm pulling that b to the x out in front of the limit. And you might be saying to yourself, wait a second, the only thing that I can take out in front of a limit is a constant multiple, right? No variable stuff. But b to the x is constant with respect to h, right? There's no h stuff in b to the x, so I can pull it out in front of that limit. B to the x is constant with respect to h, right? There's no h stuff in b to the x. All right. And then from here, something kind of magical happened. The derivative evaluated at 0 showed up. The slope of the tangent line when x is 0 showed up. Let's recall that definition, right? F prime of 0 is the limit of rise over run, f of 0 plus a little bit minus f of 0 all over your little bit, all over your run, as run goes to 0. That's what the derivative at 0 is from the limit definition. And for this function, f of 0 plus h is just f of 0. Well, f of 0, oh, sorry, I said f of 0. I meant to say f of, what's 0 plus h? It's h. It's f of h. And for my function, b to the input, we'll just have b to the h. Minus b to the 0 all over h. And b to the 0 is 1, because b is a number that's not 0. So b to the h minus 1 all over h. That's what's right here. All right, so what we have right now is a work in progress. We've just shown for any exponential function, if I look at the limit definition of the derivative, it simplifies down to the exponential function itself times f prime of 0. Right? There's your function itself, f of x, the y coordinate, times f prime of 0, and f prime of 0 is that slope of the tangent line at the point x is 0, y is b to the 0, y is 1. So here's our work in progress. For any exponential function, its derivative, the slope of the tangent line at any point on the curve, is actually just the y coordinate there, b to the x, times whatever the derivative at 0 is. The slope of the tangent at the point 0, f of 0. What is that point? That point is 0, b to the 0. That point is 0, 1. Pretty neat work in progress. So what we're saying is for any exponential function, how about I graph something with exponential growth? My base is larger than 1. Y is b to the x. The slope of the tangent line at any point on this curve is just that y coordinate there times the slope at the point 0, 1. So if I'm out here, for an example, and I want to know what the slope of the tangent line is out here, all that I'm going to need is to take the y coordinate for that point, x comma the y coordinate, b to the x. I'm going to take that y coordinate and I'm going to multiply it by the slope at that particular point. Yeah, because that's what we got. We got our y coordinate times the slope of that tangent line at that point. X is 0. What the heck is y? Y is b to the 0. Y is 1. Pretty neat. Right, so in our next, this is again a work in progress. We're going to be able to figure out in our next lesson using chain rule that for any exponential function, b to the x, the slope of the tangent line at the point 0, b to the 0, at the point 0, 1, maybe I even want to write that, 0, b to the 0, is the point 0, 1, that slope ends up being the natural log of the base. But we're not ready to actually prove that. So this is a work in progress. What I want to do now is I want to use this geometric understanding to explore the exponential function e to the x, the natural exponential function. Okay? So let's try to figure out what the slope of the tangent line at the point 0, 1 is for the function e to the x, where e is that number between 2 and 3, that number that is a little bit closer to 3. E is about 2.718. All right, so here I graphed on Desmos your e to the x function. Here's your f of x or your y equals e to the x. And at the point 0, 1, which is the point 0 e to the 0, right? What does the slope of this tangent line look like it is? If you're looking at it programmed, you already know, but let's just look at what this slope is. I'm going up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. The slope of that tangent line, the slope is 1. And in fact, you can see right there that that is the line that I graphed. Okay, what is the slope of that tangent line? It's the derivative when x is 0. Right? F prime of 0 is 1. And that's one way that we can actually think of that number e, 2.71. E is the number such that what? The slope of the tangent line to what curve? To y equals, or f of x equals e to the x at the point 0, 1, right? 0 e to the 0. At the point 0, 1, the slope there is exactly 1. We can get a limit definition of e that way, because what we're saying is f prime of 0 is 1. When I say the slope of the tangent line at the point 0, 1 is 1, I'm saying that the derivative when x is 0 is 1. What is the definition of the derivative at 0? It is the limit of rise over run as run goes to 0. F of 0 plus h minus f of 0 all over h as h goes to 0. And since I am using f notation here, I'm going to write the line instead of the curve y equals e to the x. I'm going to name it f of x because I'm using function notation. Okay, what is this? It is just the limit as h goes to 0. F of 0 plus h is just f of h when my function is e to the input and I put in h, I just get out e to the h minus f of 0 is e to the 0, and e to the 0 is 1 all over h. So this is one definition of the number e. It's the number such that this limit is equal to what? Is equal to 1. The slope of this tangent line right up above here is a slope of 1. And we have that in our text. That's one way to define the number e. It's the number such that the limit as h goes to 0 of e to the h minus 1, all divided by h, that limit is equal to 1. It's the number that makes that a true statement. Kind of cool. Right? One thing that is so special about the derivative of e to the x, if we come back to our exploration, our work in progress here, we found out that the derivative of any exponential function was the exponential function itself, was the y-coordinate, times the slope at the point 0, 1. And for e to the x, the slope at the point 0, 1 is 1. So the derivative of e to the x is just so cool. It's its own derivative. Maybe we just put from our work in progress here, we know that the derivative of e to the x, because it's an exponential function, it's e to the x times that slope at that point 0, 1. I'll just say at x is 0. And we know what that slope is. That slope is 1. So it's just e to the x. Wow. Okay. And the reason why I'm just doing red here is just from that work in progress. Right? We learned that the derivative of an exponential function was the exponential function itself times the slope at the point 0, 1. And since the slope at the point 0, 1 for e to the x is 1, we get that e is its own derivative. Sweet! Delightfully fun. So let's do one example now using this derivative rule. Oh no, I'm having you, I'm having us really believe it here. All right, so in that example, I'm having us confirm this by graphing on Desmos. So here's the function, f of x is equal to e to the x. And your teacher can't type. There we go, there's e to the x. My point of tangency, I'm going to let roam a f of a, and I'll have a be a slider so I can move that point around. Whee! Okay. And then the equation of the tangent line better be y minus the y-coordinate. If my function is e to the x at a, the y-coordinate is e to the a, is equal to the slope. Well, the slope of e to the x is e to the x. So at a, the slope is e to the a. The slope is the y-coordinate there, times x minus a. Check it out. This wouldn't work if we didn't have the right derivative, right? Look at what we have right here. The derivative, the slope, is the y-coordinate there, right? And just for practice, y minus y1, y minus f of a is equal to the slope, f prime of a, times x minus x1 times x minus a. Oh yeah, we've got the tangent line. Green and blue are the same. Okay? Right? So now, that observation, this is really, really cool. For the function the slope of the tangent line at any point at a f of a at a comma e to the a at any point is just the y coordinate there. Very, very, very cool. Right? The slope is just the y coordinate. So what is the slope of the tangent line to y equals e to the x at the point 2e squared? The slope's just e squared. Done. Pretty, pretty delightful. If I come back to this sketch here for a quick second, right? Look, the y coordinate here is 1 and the slope is 1. You know, when you put in 1 comma e to the 1 comma e, right here at 1 comma e, the slope of the tangent line is e. You know, when you put in minus 1, e, we get e to the minus 1, we get 1 over e. The slope right here is 1 over e. What a beautiful function. All right? Hope you enjoyed this video. We did a lot of thinking, but look at how delightful the rule is. Super simple. The derivative of e to the x is e to the x.